Good afternoon, everyone. Today we are going to continue the final session for the normal shock topic. So basically, we have already gone through for 2 weeks to look into the normal shock in terms of compressible flow. Okay, so we have already discussed about the overview, and then we look into the basic normal shock equations, and then we also look into the speed of sound. And basically last week, in week number 4, we also look into the spatial forms of energy equation when it's a flow compressible, as well as the topic 2.6, which is calculation of normal shock wave properties. Okay, so as I highlighted in my lecture last week, that the examples for calculation of normal shock waves will be discussed today, and we will look at several examples in relation to the normal shock wave properties, and then we will also continue to the last subtopic of normal shock wave, which involve in the measurement of velocity in a compressible flow, and then we will end up our session by having a short summary. All right, that is the plan. Okay, so let me go into the first example. All right, so in terms of the theory, we have already looked at several important equations that are normally being used when we experience a normal shock wave problems. So from time to time, I will highlight again the important equations, right? Normally in examination or any situations, you are going to be given the set of equations. I hope that that is also happening in your place. All right, so let us look into the example 2.9. Again, just to let you know that the example are being the numbering here are being readjusted to suit into our chapter. Okay, if you go into the Anderson book, it is in chapter number 8. The examples are chapter number 8. The numbering are also slightly different. So let us consider a normal shock wave in air where the upstream flow properties are given as follows. So we have the U1 to be 680 meter per second, T1 equal to 288 Kelvin, and the pressure 1 equal to 1 atm. So you have to calculate the velocity, you have to find the temperature, as well as the pressure downstream of the shock. Okay, what does that mean? Is basically you want to find the values of V2, U2. U1 is given. You're going to find U2. You're going to find T2 as well as P2. All right. So if we look here, as we know already, the expression for the speed of sound A1, which is equal to the square root of gamma RT1. So you put the numbers. So we know that the gamma for air is 1.4. The gas constant for air is 287, and the given temperature T1 upstream of the shock is 288 Kelvin. So you will obtain the value of the speed of sound to become 340 meter per second. So using the expression for the Mach number, so M1 equal to U1 over A1. So we know already the U1 given here 680 meter per second. So you divide by the speed of sound 340, you will get the value of Mach number to become 2. All right. So you have found 2 already. So we know M1 is 2. So we want to find what is the corresponding values downstream of the shock. So let us look into Appendix B. All right. So Appendix B are the set of tables, okay, given in the any textbook on aerodynamics. So And let me just go into later on. I will show you the appendix B because I didn't copy it here, right? So from appendix B, okay, so we have these values, P2 over P1 equal to 4.5. So we have the pressure ratio, okay, given at Mach 2, right? So we have that pressure ratio is equal to 4.5. We also have the temperature ratio when M1 equal to 2. So you have 1.687, and the corresponding M2, which is downstream of the shock, equal to 0.5774. So from there, we will get the corresponding value of P2 because we already know what is the value of P1. Okay, P2 over P1 is 4.5. So you times 1 ATM. So we have this value of P1, and you get P2 equal to 4.5. It is the same. So it is the value that is obtained over here. And then you can also find the value of T2 and downstream temperature by inserting the value of T2 over T1, 1.687, and times the 288 Kelvin, you will get 486 Kelvin. So the temperature has already raised from T1 to T2 to become 486 Kelvin. Right. And then you can now find the value of speed of sound at 0.2, which is the downstream of the shock. Okay, using the same expression, you will then obtain 442 meter per second for the speed of sound immediately after the shock. Okay, so because you already know the temperature, which is 486 Kelvin. Right. Using the same expression here to find the U2, okay, we rearrange that U2 equal to M2 times A2. You already have the value of M2 from appendix B, okay, at Mach number equal to 2, and then times the velocity of sound at 0.2, you will obtain velocity at 2 to become 255 meter per second. All right. So basically, if you read the correct values from appendix B, okay, you will then get the corresponding correct values. And let us just try to swap to the appendix B for a moment. Okay, so now I'm showing the appendix A from the textbook. Okay, so I hope it is there. If it is not there, do let me know. All right, I'm scrolling down to show appendix B. So in appendix B, we have already looked at this table before. So this is a table for normal shock properties. Okay, it gives you the value of Mach number, the ratio of pressure, the ratio of density, ratio of temperature, ratio of P02 or P01, okay, and then the ratio of density the pressure 02 over P1, and the value of M2. All right. So if we read over here, okay, where the Mach number equal to 2, this is the Mach number. Let me just try to highlight it with a color over there. Okay, so we have Mach number equal to 2. So we then read the corresponding ratio of the pressure, P2 over, let me just enlarge it a little bit so that you can see. So ratio of P2 over P1 equal to 4.5. You have to times 10 to the power of 1 over here. And then you have the corresponding value of the Mach number at point number 2. At the same time, we also have the value of the temperature ratio at T2 over T1. So those values are being used in our example just now. So meaning that each time you are trying to solve, sorry, this is not the right one. Okay, delete this one. So this is the correct one, and this is the M2. So by looking at the given values, we are given M1 equal to 2, and then you are going to collect all these values, the values respectively for the pressure ratio, the temperature ratio, and the M2. Okay, so now I'm moving back to the PowerPoint slides. All right, so those are the values that we already collected. We have already collected, and we read the values from Appendix B. Okay, let us move into the next example, example 210. Okay, now we need to consider a normal shock wave in a supersonic airstream where the pressure upstream of the shock is given as 1 atm. All right, so upstream 1 atm, and you have to now calculate the loss of total pressure across the shock wave when the upstream Mach number is given as, there are two conditions over here. The first condition is M1 equal to 2, right? You have to calculate that first, and then you then continue at another condition where M1 equal to 4. And then later on, you need to compare these two results and then comment on their implication. Okay, let us look into the first condition, all right, where M1 equal to 2. So the upstream total pressure is obtained from this expression. Again, this is the expression that we normally use for the condition of this situation. All right, this is before the shock wave. So we then use Appendix A for M1 equal to 2. Right, so we are going to go into Appendix A and then look into the value of Mach M1 equal to 2, and then we will then get the corresponding P01 over P1. So then we will collect the value there, 7.824. Then you can obtain P001 to become 7.824 atm. So the total pressure behind the normal shock is obtained from this expression. Okay, you have to look carefully here. This is P01 over P1 times P1, and then this is behind the normal shock. We can then get the total pressure P02, which were equal to P02 over P01 times P01. So this is basically, if you cancel it out, you will get the value of it is equal to P02 over there. So right after the normal shock, okay, you are going to use Appendix B, because we need to use Appendix B when we already cross the shock wave. Okay, for M1 equal to 2, where we have in Appendix B now, okay, we have P02 over P01, which is equal to 0.7209. So then, using the expression that we have already looked just now, we can then obtain the value of the P02, which is 5.64 atm. So to find the total loss of pressure, so you just divide the difference between P01 and P02. So we have already found P01 to become 7.824 and P02 to become 5.64, which is equal to the total loss of pressure is 2.184 atm. All right, so let's say later on we are going to go into the Appendix A and see where those values being obtained. But now we continue first for the part B. earlier the M1 equal to 2, now the M1 equal to 4. We have already increased M1 equal to 4, and you then look into appendix A again. So you will find P01 over P1 value at mark equal to 4, and you then obtain the value, corresponding value for P01 to become 151.8 atm. Okay, then using the same approach, and the total pressure behind the normal shock is obtained from appendix B for M1 equal to 4. So you can then read the corresponding value for M1 equal to 4 respectively. So you have the pressure ratio value of P02 over P01, and then which is read to become 0.1388, and then you just time P01 that you already obtained earlier. Okay, so into here in this expression, so you will then obtain the value to become 21.07 atm. Okay, so the total loss of pressure, okay, the loss of total pressure now already different, because it is at a different Mach number. So P01, P01 151.8 minus P02 21.07, you then obtain the total loss of pressure, which is greater. So you have 130.7 atm. So a note being given over there, in this example, we see that for a normal shock wave at Mach 2, and the loss of total pressure was only 2.184 atm, whereas simply doubling the Mach number, so you double the Mach number from 2 to 4, the total loss of pressure was 130.7 atm. Okay? So the moral of the story is that if you are going to suffer a normal shock wave in a flow, everything else being equal, and you want the normal shock to occur at the lowest possible upstream Mach number, so that you will not occur a greater total pressure loss. All right. Okay. So let us look into before we go there, maybe as I said, we want to look into the appendix A, so that we can confirm that the values are equal. Let us look into appendix A for the first situation. Appendix A, when Mach 1 equal to 2, you get these values. So let me just switch to appendix A. So appendix A is given is actually the isentropic flow properties. Okay, this is appendix A, which is in page 1079. So when Mach number equal to 2, so you go into Mach number equal to 2, which is over here, right? So you have Mach number equal to 2 over there, and then you can read the corresponding P0 over P, okay, 0.7824, okay, which is given 7.824 over there, right? So and then we, okay, this is the value, right? Okay, 7.824, right? And then we look into appendix B, and when M1 equal to 2, right? So then you switch into appendix B, okay, appendix B, where so we have already looked at it before, but this time you are going to use this value, 7.209, P02 over P01, okay? So 0.27209, okay? So then you will obtain that P02 values, okay? So similarly for appendix, for the M1 equal to 4, okay? For appendix B, you use the value 0.1388, okay? You go for 0.4 now, 4, Mach number 4, Okay, so the corresponding value is 0.1388 values. At the same time, for the appendix A, when Mach number equal to 4, okay, Mach number equal to 4 over there, you have the value of P0 over P, which is equal to 151.8. Okay, so where this is the values that I read just now, 151.8. Okay, so I understand that sometimes you make mistake, you read the wrong values from the appendix, and then you will get wrong answers. So that's why we want to be careful which values need to be extracted from which table. Appendix A, isentropic fluid properties, and then for appendix B, which is the normal shock wave appendix. All right. So let us continue to the next example. For example 211, right? Being given here a figure of a ramjet, a schematic of a conventional subsonic combustion ramjet engine. I hope you have already gone through your propulsion subject. If you are not, haven't take the subject yet, maybe you want to look at a different type of there are different type of engine, gas turbine engine. So, and then we have the normal jet engine, we have ramjet, we have scramjet engine, which travels at a very high speed. All right. So in this figure, the ramjet is shown in a supersonic free stream, right, where the Mach number is more than 1. And so we have the Mach number free stream, the pressure free stream, and the temperature free stream ahead of the engine inlet itself. So the portion of the shock just to the left of point 1, so just immediate before the air going into the inlet of the engine, right, where we experience a normal shock. So we have a shock being developed in front, upstream to the inlet of the ramjet. So after passing through the shock wave, the flow from point 1 to point 2. So imagine the flow travel from point 1 to point 2 before it goes into the combustor and travel into the nozzle and exited the engine, which is located at the entrance to the combustor, is assumed to be isentropic. All right. So the ramjet is flying at Mach 2, given the free stream Mach number is Mach 2, altitude also being given at 10 kilometer, where the air pressure and temperature are given also. So the pressure is 2.65 times 10 to the power of 4 Newton meter square, and the temperature is the 223.3 Kelvin respectively. So you have to find the temperature, air temperature, as well as the pressure at point 2. What is the value of the temperature at point 2? What is the pressure at point 2 when the Mach number at this point is 0.2? So basically, air travel before it goes into the engine to be Mach 2, but when it reaches point 2, it reduces to Mach 0.2. Okay, so how to approach that? So the total pressure and total temperature of the free stream at Mach number free stream equal to 2 can be obtained from appendix A, right? So from appendix A, so you have the Mach number free stream, right? 0 free stream. So you basically get this value, P0 over P, all right? So this is the value. So basically, let's just go into appendix A now, okay, so that you can so even though it doesn't mention P0 free stream over there, so but at Mach number 2, you just read this value, P, the ratio of the pressure, P0 over P, which is P0 free stream over P0 to become 7.824. Okay, I'm going to go through and forth throughout our example so that you know exactly where the numbers coming from. And you put in the value of the pressure, the pressure to the pressure 2.65 times 10 to the power 4 Newton square meter, and you then obtain the free P0 free stream to become 2.07 times 10 to the power 5 Newton per square meter, right? Then you can now obtain the value of the temperature at T not free stream. At T not free stream, basically you can read the value from Appendix A. Appendix A again, this is the value coming from the free stream 1.8. Okay, so let us go into the so this is the value, okay, 1.8, right? So I hope you can also flip into your own textbook or your own soft copy of the book so that you can follow through the example that I'm giving you now. All right, so and then eventually you just put inside the values of T infinity. So because we already have the value given given T infinity before it goes into the engine, which is 223.3 Kelvin. Okay, so at point 1, now what happened? Behind the normal shock, the total pressure from Appendix B. So we then now go into Appendix B. So by using the same expression, you have the value of P0 1 over P0 infinity to become 0.2709, right? So if you go for at Mark 2 in Appendix B, right? So let us go slow, all right? So you have P02, okay, this is the value, okay? So this is the value, 0.7209, and then times the value of P pressure 0 free stream, given to be 2.07 times to the power 10 to the power of 5. So you have already obtained P0 free stream earlier. So you plug in the number inside here, then you get the value of the pressure 0.1 at position P01. So 1.49 times 10 to the power of 5 Newton per square meter. Right. So the total temperature is constant across the shock. So we know that the total temperature is the same. T01 equal to T0 infinity, which is 401.9 Kelvin. So the flow is isentropic between point 1 and point 2. Hence, the pressure P0 and T0 are also constant between these 2 points, right? So therefore, P02 also read 1.49 times 10 to the power of 5 Newton per square meter, and T02 also being read as 401.9 Kelvin. Okay, because of the isentropic condition between these 2 points. So at point number 2, we are also being given the value of Mach number, M2 equal to 0.2. So the ratios of the total to the static pressure and total to static temperature from Appendix A, okay, when we read it from Appendix A at Mach 0.2, right? Let us go into Appendix A now, right? So we go to Appendix A at Mach 0.2, right? Mach 0.2, which is here, 0.2. This is Mach 0.2. Okay, so we also have the values of pressure ratio and the temperature ratio, right? So you use those numbers, right? This number and this number into the expression, you will get P2 pressure at position 2 is 1.45 10 to power of 5 Newton per square meter, and the T2 value to become 399 Kelvin. Okay? Right. So recall that at 1 ATM, which is equivalent to 1.0210 times 10 to the power of 5 Newton per square meter. Hence, P2 in ATM, okay, which is you just divide that value, P2 values over 1 ATM, which is 1.42 ATM. Okay, so a note also being given there. Air pressures and temperatures on the order of 1.42 ATM and 399 Kelvin entering the combustor are very tolerable conditions for low speed subsonic combustion. So in example 2.9, just now we will draw a comparison between this result and the condition that would exist at a much higher free stream Mach number. Okay. Now, I hope you can follow, and maybe right after this, we do not have to go to Appendix A and Appendix B, but just to get you are aware that you have to ensure that the values are taken correctly. If you, again, the decimal places, pay attention on the decimal places, pay attention on the values that you take, either from Appendix A or from Appendix B. Okay, so now example 2.12, repeat example 2.11. Okay, except for the free stream Mach number now is given to become 10. Earlier it says at 2, now it increases to 10. Assume that a ramjet has been redesigned, so the Mach number at point 2 remains equal to 0.2. Okay, the Mach number at point 2 is still remain at 0.2, but the free stream Mach number already increased to 10. From Appendix A, when Mach number equal to 10, we have the value of P naught over P equal to 0.4244 times 10 to the power of 5. So you put inside the numbers back, you will then get the value of P naught infinity. You can see that the pressure are quite high. So, and then the T naught infinity, right? So you can get the value from Appendix A at Mach number 10, the temperature ratio, and you will then get the value of the temperature to become 4,690, which is very high. Very high pressure, very high temperature at the same time. So what happened at point 1 from Appendix B, where we have Mach number free stream to be 10. So when we look at Appendix B, so the corresponding pressure ratio as well as the P stream Mach number, you will then get P01 to become 343.10 to power of 6. And since taking the T01 equal to T0 infinity, because it is isentropic, you will then get the value to be the same, 4,690 Kelvin. So at point 2, when M2 equal to 0.2, we have from example 2.6 earlier, right? So we have the corresponding pressure ratio and temperature ratio. Also at point 2, since the flow is isentropic between point 1 and 2, right? So you can also get the value of P02, which is equal to P01, and T02 equal to T01. So we have the same values over there. Hence, what happened? You can then now get the value of P2 and the local pressure value at P2 to become 3.34 times 10 to the power of 6, and T2 is 4,653 Kelvin. So in terms of atmosphere, P2 become 32.7 ATM, which is considerably very high compared to the rather benign conditions at point 2. So it's not which is existing for the case treated in example 2.11, right? So in the present example, the air entering the combustor, it is at the pressure and temperature of 32.7 atm and 4653 Kelvin, which is both extremely severe conditions. So this is a very high conditions, above the melting temperature of titanium even. The temperature is so hot that the fuel injected into the combustor will decompose, okay, rather than burn, with little or no thrust being produced. So imagine that will happen. Moreover, the pressure is so high that the structural design, as I said just earlier, of the combustor would have to be extremely heavy, assuming in the first place that some special heat resistant material could be found that could handle the high temperature. All right, so when you are designing this kind of jet engine, ramjet, at very high temperatures, you have to consider what are the pressure associated with it and what are the temperatures associated with the flight regime. Okay, let us move into the next example. Example 213. Okay, the pressure ratio across a normal shock wave is given as 4.5. You have to find what are the Mach numbers in front and behind the wave. Okay, you have to find what is the Mach number in front of the shock wave and behind the normal shock wave. At the same time, you also need to find the density and the temperature ratios across the wave. So again, using Appendix B, because it is a normal shock wave problems, you have pressure ratio being given there. So at pressure ratio P2 over P1 equal to 4.5. So you can then find the corresponding Mach number to become 2, and M2 is 0.5774. So if we again go into Appendix B, find for pressure ratio 4.5. So you go to Appendix B now. We just quickly go to Appendix B, right? And stop at Mach number equal to 2, right? So you have the pressure ratio, go to Mach number, go to pressure ratio 4.5. So you will find the Mach 1 to become 2 and the Mach 2 to become 0.5774. All right, so those are the values that are needed. Also from the same table, you can then get the density ratio and the temperature ratio. All right, so quite straightforward. So you have to find the density ratio and the temperature ratio across the wave, which is obtained from the table. So note here, for a normal shock, the specification of the pressure ratio across the wave uniquely determines the Mach number in front of the wave. Okay, so the Mach number behind of the wave, at the same time, the ratio of all other thermodynamic properties across the wave. So you can use the table to find the values of Mach number, density, and temperature ratios if you know the pressure ratio across the shock wave. All right. Moving forward, going into example 214 now. The temperature ratio across a normal shock wave in the air is 5.8, right? So now we want to find what is the corresponding value for the Mach number, density ratio, and pressure ratio. Let us go into Appendix B now. So at at the temperature ratio of 5.8. So go to this Appendix B. So we want to look at the temperature ratio, which is equivalent to 5.8. Okay? So 5.8. So basically we will stop there. Okay, so from there you will then get the corresponding Mach number, M1, M2, right? So you have M1, M2, and then from the same table, density ratio and the pressure ratio. All right, so Note here, for a normal shock wave, the specification of temperature ratio is uniquely determined the Mach number in front of the Mach of the wave and the Mach number behind the wave, and the ratio of all other thermodynamic properties are also can be obtained. Okay. Another example, 215, before we have a short break, right? Because we have already gone through a few examples. Okay, let us just finish up this example. Mach number behind a shock wave of 0.4752. And now they give us Mach number behind the normal shock wave. So what is the Mach number in front? Okay, so basically from appendix B, behind the shock wave is 0.4752. Let us go into the table. Okay, we find 0.4752, 0.4752, which is this one, right? So, and then you will then get the value of Mach number in front to become 3, and the density ratio 3857, right? 3857. And the corresponding pressure ratio and temperature ratio also can be obtained. All right. Okay. So we are going to look into a couple more of examples. So before we move on to the 2.7, so let us look into example 2.6, 2.16, 216 now. And the velocity and temperature of the flow ahead of normal shock waves are given as 1,215 meter per second and a temperature of 300 Kelvin respectively. So you have to find the velocity of the flow behind the shock. So I just underline the word behind there, okay, so that we can know which appendix that we need to view. Okay, so by finding, first you have to find the speed of sound. Okay, A1, right? Putting the value of 300 Kelvin over there, you will get the speed of sound to become 347.2 meter per second, and the corresponding M1 to become 3.5. Okay, from from appendix B, at Mach 1 equal to 3.5, you will then obtain M2 to become 0.4512 and the temperature ratio of 3.315. So if you go into the appendix B, you will get these values. So putting the value, finding the value for T2 now, right? So you can now get the value to become 994.5 Kelvin by knowing this is the value. So of the temperature ratio, okay, and then you can now obtain the value of the speed of sound at station 2 to become 632.1 meter per second by putting the value of the temperature T2 inside this expression. Finally, you will get the velocity, velocity at U2 to become M2 is 0.4512 times the speed of sound at station 2 to be 285.2 meter per second. All right. So there's a note over here. Unlike the previous 3 examples, we have already looked at the previous 3 examples where only one dimensionless quantity, either given M1 or M2 or P2 over P1, the pressure ratio or any other values uniquely specified the shock wave. However, in this example, 2 quantities are needed. And this is because we were given actual dimensional quantities. We are given velocity as well as the temperature ahead of a normal shock, right? So just the velocity value only, if you are being given only the velocity, you cannot you cannot solve the problem. You cannot, which is not define a specific normal shock. So we need both quantities. We need the velocity, we need the temperature in order for us to solve the problem. So first we need to calculate the Mach number from the given velocity and the temperature. Emphasis is again made that Mach number, which is not the velocity, is the powerful single quantity that specifies a particular normal shock. All right, move on into the next example. Okay, example 217. The velocity and temperature behind a normal shock were given as 329 meter per second and 1500 Kelvin. So you have to calculate the velocity in front of the shock wave. Now it is in front. Okay, so again, finding the A2, right? So you will get the speed of sound at station 2 to become 776.3 meter per second, because this is a velocity and temperature behind the normal shock being given. Now you have to find what is happening before, in front of the shock wave, right? So you can now get the M2 values to become 0.4238. Examining Appendix B, right? So if you look at Appendix B 4.238, let us just quickly go to Appendix B and find where is 0.4238, right? So this is Appendix B, 0.4238, 0.4238. Okay, you could not find the exact number 4238, right? So 4236 and 4245. So you have this value 4245 and 4236. Okay, you want to, there's no precise entry for 4238. So you can then use the Mach number before and after, right? By interpolation, you will then get the values, right? So M1 now become 4.4898, right? So it is in between those values. So basically it is in between this, between this and this, right? So you can then get it to become 4.48998. From Appendix B, we note that T2, the pressure temperature ratio at M2 equal to 0.236 to 4236, and the temperature ratio 4788 at M2 0.4245. You can now also interpolate to find what is the corresponding value at Mach number 0.4238. We can then find the temperature ratio of this 4856. Thus, using that value to find the temperature at before the shock, okay, T1, right, to become 308.9 Kelvin. So you can then get the speed of sound to become 352.3 meter per second. Respectively, you will get the velocity before the shock, which is equal to 1581.5 meter per second. So once again, we see that a single velocity does not specify a normal shock wave. However, a velocity in combination with temperature. So you need those two values. One is the velocity, the other one is the temperature. Then you can specify the normal shock. In contrast to example 216 earlier, where U1 and T1 ahead of the shock specified the shock, we see that U2 and T2 behind the shock also sufficient to specify the shock. All right, next example 218. Repeat example 217, but now use the nearest entry in tables rather than interpolating between entries, right? So basically, you want to see whether how accurate we can get the values of the, meaning that you do not have to interpolate, you just use the nearest entry. Using the nearest entry is less accurate because you are just assuming that it is nearer to the one value rather than the other one. Okay, but it is simpler and quicker. Okay, just to get an estimation is good enough. But if you want accuracy, you have to do the interpolation. And so we can now then compare this less accurate result with more accurate result from example 217. So we repeat example 217, where we need to find M2 0.4238. So the nearest entry to 4238 is 4236. If we look back over here, 4238 is just 2 point above 4236, okay, compared to 4245 just now, right? So that's why we are using 4236 value for M2, and we are using corresponding M1 to become 0.45 and the respective pressure and the temperature ratio. All right. So putting those value, taking the temperature ratio at Mach number equal to 4.5, right? So you get a temperature T1 equal to 307.7 Kelvin. You then get the speed of sound at 1 to become 351.6 meter per second. So then the velocity become 1,582 meter per second. So you compare the two results using the interpolation method and the nearest entry method. So you get very close to each other. Basically, it's 0.06% error. All right. So not that significant, but it is, if you, for accuracy reason, you will then use the interpolation method. But for estimation, you can just live with the nearest entry method. All right. Example 219 now. Okay, consider a normal shock with upstream of Mach number 3.53. Obtain the downstream Mach number by using the nearest entry. You have to use the nearest entry first, and then use the interpolating tabulated values, and then exact analytical calculation. So there are three methods over here, and then compare the accuracy of the results. The first one, nearest entry in Appendix B for Mach number 3.55, using the entry in the table. So we go to Appendix B, Mach number 355. Appendix B, Mach number 355. So 355 is there, all right? Okay, so we use this value, 355. Okay, use the M2 over here, right? So for the second approach, interpolating of tabulated values, because we want 353 just now, so we just use 355. Okay, right? We want 353, we just use 355. So the next step is to interpolate between 350 and 355 to get 353. All right. So comparing the two, comparing values at 355 and 350, right? Interpolating the values corresponding to it. So you get Mach number 0.45 instead of 0.4492, all right? Which is quicker, but this one you have to do some calculation over there, right? So using equation, so we know already for normal shockwave situation, you can also use this equation. So where we can find M2, which is equal to become 0.45. All right. As a conclusion, Mach number to compare the result, nearest entry 0.4492, interpolation you get 0.45, exact solution using equation 0.45. For all practical purposes, all three approaches yield almost identical result. All right, so meaning that you can use either one depending on the type of accuracy that you require. Okay,